Hello everyone, this is my microprocessor final project, and now this part is the finite state machine with its 4 output stages. This is the main clock line which connects to all the registers I use. This is the main clear line, which when I push this button, it will clear all the information stored in every registers. And this is the reset, which will reset the finite state machine to stage 0. And now this part is the instruction counter. It's basically like 4 falling edge registers. When I start the clock, like after each clock cycle, you can see this display. The output information will come up to 1. It's now 2 and then 3, and it connects to the instruction memory and the data memory. So when it counts, the information in this memory will be selected to the next bit. And let's clear it. And then this part is the output logic. It gets information from the finite state machine, like these 4 lines, and these 8 lines comes from the instruction memory. So this is instruction, and this is finite state machine, and the output logic through some gates will get to the multiplexer of each registers or those tri-state buffers or anything else. And this is the instruction memory. Its output goes to the instruction registers and then goes to the output logic. And this is the data memory, which stores the data associated with the instructions, and its output is to the data register and controlled by those tri-state buffers to write on the bus. And if we reset the simulation, you can see all those blue lines are the main bus line. And then here, the calculation part. This is the input register. It gets information from here. That's a constant, and this is the input display. Its information goes directly to the input register, and when it receives the E in I in signal, it will enable those tri-state buffers so it can write on the bus. And this is output register. It basically gets information from the bus and then directly output it to this output display. It's here. And this part is the register A. It has many functions. First, it can receive information from the bus, like here. When the multiplexers receive the 1 signal, and also its output will always connect to here. That's the input A of the ALU. And also when it receive a signal 1 in those tri-state buffers, it will be able to write its own information to the main bus line, the blue one. And this part is the register B. It has like fewer functions than register A. It can only get information from the bus but not write on the bus. And the same, the information stored in it will goes to the input B of the ALU. And that's the ALU. The main part is 4 full adders. This one is the least significant, and this one is the most significant. And this part, those multiplexer, is used to do the add and sub function. When it receives the 1 through those lines, it will become A minus B. Use the 2's complement rule. Now let's do some tests to test the overall function of this microprocessor. As I wrote in the report, I will use this set. It's 3, 1, 2, 4. Let's do 3, 1, 2, 4. 5, 2, 1, 0. That's 4. That's 0, 5, 7, 6. and that's 9740. Okay, now let's start the simulation. I will use Ctrl T to do it second by second. So the first instruction is 3, which is get input from the input pin and store it in register A. Here. Now let's start the tick. So stage 0, stage 1, and stage 3. Now the information is already goes into the bus, and in stage 4 it will be stored in register A. So that's correct. And then the second instruction is do an add. It will add the information in the data to the register A. And we can see S0, S1, and now we can see the data 5 has already goes into the bus, and in this stage it goes to the register B, and it also enables the output of the ALU, and we can see 5 and 4 is 9 on the bus, and in the last stage it will store the 9 in the register A. This is also correct. And then let's do the instruction 2. That's basically a subtraction. Stage 0, stage 1, you can see the 7 is already on the bus, and then the 7 goes to the register B. Now we can see in this stage the add sub line it's like this bright green is 1, so it's 9 minus 7, and when we enable the output of the ALU, we can see the 2 appears in the bus, and in the last stage the 2 goes to register A. That's correct. And next is 4, which is the output command, and it has nothing to do to the data here. So S0, S1, S3, like nothing happens, but in stage 3, the information in register A is already now goes to the main bus, and the next stage it will be stored in the output register and get output to the output pin. That's also correct. And then it's 5. The command file will get information from the data register and store it in register A. So S0, that's S1, it's already 9 here, and S3, nothing happens, and in S4, it is stored in the register A. This function is also correct. And then let's do another subtraction. I'm going to subtraction 9 from 7, and S0, S1, S2 is 7 here, S3 is subtraction, and now you can see it's 9 minus 7 is 2. It's on the bus, and next stage it goes to register A. And let's do an add again. Now it's 4 here and add 2 in register A. You can see it's 4 here. The add sub is 0, so it's an add, and enable the output is 6 and store 6 in A. That's also correct. And next, the instruction is 0, so the microprocessor will do nothing. You can see this whole stage, you watch those 5 registers, nothing changes. and the last test is another output. It's 4. It will output the A to the instruction register A to the output pin. So let's do it. Stage 3. It's the information of A is already in the bus, and stage 4 it will output it to the output pin. So after all those tests, like we do nine commands, and we can see the microprocessor worked as expected.